Winter is coming, and for many, heating bills are rising faster than the temperature drops. Most people rely entirely on gas or electricity to stay warm, but what if there was a way to heat your room safely, efficiently, and without any utilities at all? One experimenter set out to create a wall-mounted heater using only simple materials, testing whether it could actually keep a room comfortable in cold conditions. But here's the question. Is it really possible to heat a room safely without gas or electricity? Or is this method more complicated than it looks? Let me know your answer in the comments below. Heating a room typically requires a reliable energy source, such as gas, electricity, or wood. According to energy efficiency studies, households spend an average of 30% of winter utility bills on heating alone. Alternative heating methods have existed for centuries, including passive solar heating, thermal mass heaters, and heat retention materials. Modern DIY enthusiasts have explored small-scale, wall-mounted heaters that rely on stored heat or convection principles rather than active energy consumption. Public records show that such systems, if properly constructed, can provide meaningful warmth while staying compliant with safety codes. Step 1. Materials and planning. The heater required only a few materials: metal sheet or aluminum panel for heat conduction, fireproof insulation board, small heat-retaining bricks or stones, mounting brackets, non-toxic thermal paint for enhanced heat reflection. The first step involves selecting a wall with proper ventilation and ensuring the structure could safely support the heater. Measurements were taken to optimize airflow and heat distribution. Step 2. Construction of the heat panel. The metal panel was mounted on top of the insulation board. Behind the panel, the bricks or stones were stacked to create thermal mass capable of storing and radiating heat. The experimenter documented airflow patterns to ensure heat would circulate naturally rather than accumulate dangerously. Expert commentary noted that thermal mass systems can store heat from minimal sources, such as sunlight or a small candle, and gradually release it over time, making them effective for small rooms. Step 3. Testing and observation. Initial tests focused on room temperature changes and safety monitoring. Infrared thermometer readings confirmed even heat distribution. No flammable materials were near the heater. The room temperature rose steadily over several hours from passive heat sources. Observations. Thermal mass retained warmth for up to 4 to 6 hours after heat source removal. Convection currents improved circulation without fans or electricity. Safety measures included fireproof walls, monitored insulation, and a smoke detector. Step 4. Refinements for efficiency adjustments included angling the panel slightly for better airflow, adding reflective paint to enhance radiation, adjusting stone or brick placement for optimized thermal retention. Peer reviewers in DIY and engineering forums confirmed that these refinements significantly improved performance without adding energy costs. Step 5. Legal and safety considerations. Building codes often require non-combustible wall materials near heating elements, proper mounting to avoid structural failure, fire safety compliance. One interpretation is that small, wall-mounted passive heaters are legal for residential use if constructed with fireproof materials. Another perspective emphasizes monitoring and regular inspection to prevent accidents. Disclaimer: this is for informational purposes only, not legal advice. Initial setup demonstrated that a room could maintain warmth without gas or electricity. Expert review confirmed proper material use and safety compliance. Refinements improved heat retention and airflow efficiency. Long-term monitoring showed sustained warmth without any external energy input. This experiment proves that it is possible to heat a room without utilities, using only clever design, proper materials, and thermal mass principles. With careful construction and adherence to safety guidelines, DIY wall-mounted heaters can reduce reliance on gas or electricity and lower heating costs. Final question. Do you think DIY heaters like this can replace traditional heating safely, or are they too limited for practical use? Share your thoughts in the comments below. Winter arrives, and for countless households, heating bills skyrocket as temperatures drop. Most rely entirely on gas or electricity, but one DIY experimenter asked a simple question. Can a room stay warm without any utilities at all? Using only a wall-mounted panel, fireproof materials, and thermal mass, they set out to test whether a practical, safe, and energy-free heater could actually work. But here's the question. Is it really possible to heat a room safely without gas or electricity, or is this method more complicated than it looks? Let me know your answer in the comments below. Household heating consumes roughly 30% of winter energy costs, according to energy efficiency studies. Traditional heaters rely on gas, electricity, or wood, which come with financial and environmental costs. Alternative methods, such as thermal mass heating, have existed for centuries. This principle stores heat in dense materials like stone, brick, or metal and gradually radiates it into the room. Modern DIY enthusiasts have explored wall-mounted designs using passive heat retention to reduce dependency on utilities. Local building codes allow passive heating systems if they meet fire safety standards and use non-combustible materials. Commercial and residential regulations stress proper mounting, insulation, and airflow management. Month 1. Planning and materials. The experimenter carefully selected materials, metal panel, aluminum or steel, for heat conduction, fireproof insulation board, to protect the wall and reflect heat, heat-retaining bricks or stones, to store and radiate warmth, mounting brackets, for secure installation, thermal reflective paint, to enhance radiation. Observations and notes. Wall selected was non-combustible, structurally sound. Room size measured, 12x 14 feet. Initial airflow patterns analyzed to avoid hot-cold spots. Month 2. Constructing base and panel. Mounting the insulation board. Ensured a 2-inch gap between wall and board for airflow. Stacking bricks or stones. Arranged for maximum surface area contact with the metal panel. Mounting the metal panel. Secured above thermal mass with brackets. Ensured panel was level. Test observations. Wall-mounted structure supported full weight without shifting metal panel, slightly angled to allow natural convection currents. Expert insight. Thermal mass systems work best when airflow is consistent. Angled panels create natural upward airflow, distributing heat evenly. Month 3. Initial passive heat test room temperature recorded before test. 18 degrees, 64 degrees. Heat source. Sunlight through windows. Small candle placed behind panel monitored for 6 hours using infrared thermometer results. Maximum surface temperature on panel, 35 degrees, 95 degrees. Room temperature rose to 24 degrees, 70 degrees. Thermal mass retained heat for 4 hours after heat source removal. Observations. Convection current visible near ceiling. Minimal heat loss to wall thanks to insulation board. No smoke, no odor, no fire hazards. Month 4. Refinements and safety checks. Angle adjustments. Panel tilted 10 degrees for optimized airflow. Bricks repositioned. Reduced cold spots in thermal mass. Reflective paint applied. Increased radiant heat efficiency by contra 10% safety checks. Confirmed fireproof spacing. Smoke detector installed. Legal compliance notes. Local building codes permit small wall-mounted passive heaters if non-combustible materials are used. Expert review confirmed structural and thermal safety. Month 5. Long-term monitoring. Daily temperature logs taken over 30 days. Average daytime room temperature maintained at 22 degrees, 772 degree, without utilities. Thermal mass remained stable. Minimal maintenance required. Observations. Minor dust accumulation on panel, wiped weekly. No structural issues detected. Convection airflow maintained uniform warmth. Peer commentary. Similar DIY designs confirmed that proper material selection and spacing is critical. Neglecting safety gaps can compromise effectiveness. Month 6. Performance optimization. Added secondary thermal panel behind bricks for added heat storage. Increased reflective surface area for better radiation. Adjusted panel height to align with typical seating and desk areas. Outcome. Heat retention improved to 6 to 7 hours after minimal sunlight exposure. Room comfort achieved even on coldest winter days. No fire hazards. No utilities required. Initial heat retention test. Confirmed concept. Worked expert validation. Ensured structural safety and compliance. Reflective paint application. Significantly improved radiation efficiency. Airflow adjustments. Prevented cold spots. Improved uniformity. Thermal mass layering. Maximized heat storage for overnight retention. Passive, wall-mounted heaters are generally legal if non-combustible. One interpretation. Legal for residential heating, particularly non-potable, small-scale rooms. Another perspective requires inspection in certain municipalities to meet building codes. Safety checklist. Proper wall clearance, fireproof materials, stable mounting disclaimer. This is for informational purposes only, not legal advice. This experiment demonstrates that heating a room without gas or electricity is possible using simple materials, clever design, and thermal mass principles. With careful construction, monitoring, and compliance with safety guidelines, DIY wall-mounted heaters can lower utility costs while keeping a room comfortably warm. Final question. Do you think DIY heaters like this can replace traditional heating safely, or are they too limited for practical use? Share your thoughts in the comments below. For more verified DIY experiments, sustainable solutions, and practical engineering insights, subscribe and hit the notification bell to stay updated.